permission to do so. Okay, good morning, everyone, or good afternoon, everyone, and welcome to the first of this year's A3D3 seminars. We took a little break after November to try and figure out a new schedule and new program, and so we have at least got speakers sorted out for the next 3 or 4 months, invited anyhow, and we have a list for the rest of the year, so that will be progressing. And the schedule is on the website, as well as we'll be sending out reminders monthly. So kicking us off again is multi-messenger astronomy, and I'm very, very pleased to be able to introduce today's speaker, Professor Niharika Sravan of Drexel University. Niharika was awarded a PhD in physics and astronomy and a graduate certificate in integrated data science from Northwestern in 2018, and she was then a postdoc researcher at Purdue University and then at Caltech, where she was my postdoc for the last 2 years before she moved on to a faculty position at Drexel just over a month ago. She is definitely an expert in the use of machine learning methods for solving problems in astronomy, and has really pioneered the development of autonomous agents for strategizing real-time observations of astronomical transients, which is a particularly important thing for us to be doing in multi-messenger astronomy as we go forward into the sort of LIGO and Rubin Observatory eras. So her work is right at the cutting edge of the application of machine learning, and well within the interest of A3D3 for how can we do this with low latency and such. So I'm very pleased that she's going to be talking about this today. So Niharika.
Hey, so if some of you have noticed, I used to be in the audience. I mean, I'm not sure in what capacity I'm still connected with A3D3, but like not more than a month and a half ago, I was still one of the postdocs associated with the institute. So it's kind of fun to now be on the speaker side. So yes, as Matthew's mentioning, I'm coming straight out of Matthew's group. We've done some really interesting work recently on thinking about how we can have intelligent agents help us to do low latency decision making for science in the context of in the particular application for thinking about multi-messenger astronomy and signals that are associated with these sources. The thing I think is interesting about the work that we have done is that we've been applying reinforcement learning methods, which turn out to be sort of the only solution, algorithmic, that can help us to actually do this in a principled and like rigorous fashion. And as I will go through a couple of examples in this talk about how you can actually have automated systems triggering additional follow-up given a particular objective. And the idea is that the convergence of those two projects eventually leads to more of the reinforcement learning approaches that we will be exploring in the future. So, but definitely, I think like for people who think about machine learning and think about how we can use some of these advanced tools to really kickstart and do discovery, do science like never before. I think a less used class of algorithms would be reinforcement learning. And I think with this talk, as I talk through sort of like what types of problems we can actually solve with reinforcement learning, I think maybe people would maybe benefit from thinking about how such approaches can be applied to the problems that they're facing, and sort of really, like I said, get at solutions that are currently impossible with approaches that are being used. So yeah, anyway, so the point of this talk is to just give you a couple of use cases of how reinforcement learning has been applied. Yeah, like maybe probably make this more of a discussion of how we can do this more in other science cases, and I would be very interested in thinking about those as well. So yeah, so my talk is labeled autonomous real-time decision making in the era of multi-messenger astronomy. I think most of us in the institute are fairly familiar with all of the various not the legs, the columns, if you will, that support A3D3, one of which is multi-messenger astronomy. So I don't think it needs much introduction, but I think since it's the only jargon in this title, I will try to introduce that a little so that everybody knows what I'm talking about. So in order to do that, I have to roll back the clock to 2016, when surveys like the Zwicky Transient Facility were observing the sky at regular intervals. And in this galaxy, not particularly remarkable otherwise, there was a source that was brightening, and that eventually faded. Now, this happens regularly, like annoying amounts of times these days, because we're pretty good at monitoring the sky. The interesting thing was that moments before, gravitational wave detectors on the ground were detected a signal coincident with this broad region of the sky where you saw this source, but it saw this source in gravitational waves. And so this type of joint detection in two different so-called messengers is an example of multi-messenger astronomy. And classically, multi-messenger astronomy has 4 messengers that you can think of that are looking at the same astrophysical source in various probes. So classically, we are all thinking of electromagnetic waves when we think about doing astronomical observations. But we also have things like we can probe the same sources in cosmic rays, gravitational waves, as I mentioned, but also neutrinos. It's just to mention that I think there's a good amount of coverage in this institute, thinking about at least these three aspects of multi-messenger astronomy. So the thing is that this is great because this type of research, this type of science has only been possible since 2017. So it's quite novel in terms of what types of science that can be extracted from this type of inquiry. But overall, I think it's interesting because multi-messenger sources are some of the most energetic and expressive in the universe. So sources of multi-messenger astrophysics, sources of multi-messengers from astronomy include things like supernovae, things like kilonovae. These are associated with mergers of compact objects, of which at least one source is a neutron star. Things like active galactic nuclei that probe a variety of physical processes that surround supermassive black holes at the centers of many galaxies, and probe a wide range of complicated physics that occur in these regions. Things like tidal disruption events, where a star, again associated with a supermassive black hole at the center of the galaxy, can experience tidal stripping and disruption that can lead to signals that are possible multi-messenger sources. So all of this is really exciting. It's new. The physics is amazing and very very awe-inspiring. The thing I want to mention and highlight in all of this is, because I think I'm going to drill more on this aspect, is that when we think about multi-messenger sources, a critical component of how we get this science done is using surveys. So here's a smattering of ground-based surveys that look at the sky in the optical. And the idea is that basically by revisiting the same region over and over again, you can look at sources that are changing in some capacity. And if you remember from the previous slide, we were talking about these like really energetic sources that are associated with the partial or complete disruption of astrophysical objects. By definition, these are things that are changing. So in order to probe them, you need to have a changing look of the sky, and surveys are really, really important in making that sort of thing happen. I just want to make sure that we all understand the type of data that we are going to be thinking about from these from these surveys, because they'll show up again and again in my talk, and just make sure that we know what this is. So imagine that this is a galaxy where there is an explosion that happens, a supernova that happens, and the supernova brightens and then will fade. What will happen is that surveys will look at that region of the sky using various filters that will be sensitive to various portions of the electromagnetic spectrum. And as a result, they don't see this whole energy output. They end up seeing something like this, where different portions of the electromagnetic spectrum are kind of like collected in various buckets and spread out. And so these are multi-channel in some sense, because they are sort of like, it's not the full spectral energy distribution, but it sort of samples various portions of the electromagnetic of the energy spectrum. But the thing to note is that we don't even see something like this, because surveys are operating on a pretty regular, pretty coarse schedule, in that they don't revisit the same region over and over again very often. So what we end up seeing is something like this. And the thing to note, I think, from the data science side is that this type of data set is kind of unique for a few reasons. One is that clearly all of these are, number one, multi-channel. So there are more than one more than one channel for the same time series. The second thing that we have is irregular sampling. So, we don't control when we obtain a particular set of observations. Due to the conditions of observing, you may or may not successfully get an observation at that time, or it may happen in a sort of like offset schedule. We've been having a lot of snow and rain in California, and you end up just having like very unreliable way, like sampling, in terms of like we not only in terms of the full light curve that we get, but in terms of when we expect to get the next observation. It's very, very hard to determine when exactly it's going to be, even though we know more or less what our objectives are going to be. So the reason I mentioned this is because whenever people try to think about doing science with data like this, we have a little bit of a difficulty in taking this type of data and immediately translating it into types of machine learning, off-the-shelf machine learning packages that we receive, because many of these actually expect some sort of like regular sampling. Another thing that we have is heteroscedasticity in terms of the uncertainties that we're receiving. So these particular idiosyncrasies sort of make it a little harder for us to sort of like immediately apply off-the-shelf solutions, and we have to be creative about how we actually recast the problem to solve our specific science case. And I think, unfortunately, this type of data is very astronomer-like, and it's very hard to actually find solutions in industry or otherwise that look like this, so we can actually do better inferencing. So for example, Matthew, and I'm sorry I'm drilling on this, but it's something that I think is very fundamental. For example, Matthew is very interested in thinking about how to get red noise parameters from some of these light curves. And the idea is that he's worked extensively on using Gaussian processes and another, sorry, which is the other algorithm, I forget. Wait, what am I thinking of here? Is the one that Weijiang's working on?
Damped random walk or Karman.
Yes, damped random walk. Yes, I'm sorry. Yes, so he's thought about a lot of these creative solutions to actually try to characterize some of these, and it's not easy. And it'll be very beneficial if there could be some generic methods that we could apply to actually get statistical inference out of time series that look like that. Anyway, spent too much time on that. Didn't mean to, but okay. So in terms of surveys, we are very excited because there's this huge behemoth of a survey called Rubin Observatory that is coming online in a few years. This is the #1 flagship of the US community and has been recommended jointly by the NSF and DOE. It has been recommended by the National Research Council and has been funded by NSF and DOE. When it starts operating, it will conduct a 10-year survey of the optical sky. The amazing thing is the amount of data that will be produced as a result of its survey. So these numbers are thrown around quite a lot, but I think I want to contextualize it for you. We will get real-time alerts of all of the discoveries that Rubin Observatory is making in most institutions in the US, for example. Thinking about the amount of data, we have about 20 terabytes of data that will be flowing in terms of the raw data volume that is collected over images. And if you want to compare this with another image-friendly service, which is Instagram, this is about, Instagram has about 20 terabytes of data per day that it's receiving. And the thing to note is that even though in raw data volumes, these are kind of like similar, in terms of like what types of data are being we're talking about are different, because most of the data that's being uploaded to Instagram are meaningful and are not somehow just complete made of complete noise. However, most of the data that will be coming out of the Rubin Observatory will be mostly noise. And the second aspect of this, which is really exciting, is this real-time worldwide alert system, where the vast majority of discoveries that the observatory will be making will be available worldwide in the matter of a minute or so. And at the end of its 10-year survey, it will have a vast library of 37 billion light curves in 6 filters or so that it will collect. I was most recently a part of this Wiki Transient Facility collaboration, which I view as the pathfinder to Rubin, especially for the types of science that we've been talking about here. And the reason I state this is because from a variety of observing conditions in terms of the cadence, in terms of the depth, this particular survey is operating about 10% of the scale of Rubin Observatory. It also is participating at for like the majority, I would say 50%, so not majority, like a vast fraction of its program participates in delivering discoveries within worldwide, not world, yes, I think worldwide within a matter of minutes. So within a matter of about 20 minutes or so, discoveries that this Wiki Transient Facility are also made public to the astronomical community. And once again, this has also been, it's a survey that has collected a vast amount of data with 20 billion light curves or so and counting, and it's a survey in about in 2 filters or so. Great. So we're all excited about this, about these surveys. But I really want to go back and think about, this issue of doing multi-messenger astronomy, and where perhaps, for example, we may be limited, and why we may benefit from doing things slightly differently. The thing to note is that the story I started off with in the start of this talk, where there was this one multi-messenger source, which was the same source that we saw in gravitational waves, there's actually only one example of its kind. And the gravitational wave detector systems have been operating for a while, and we have not been successfully able to confidently identify the electromagnetic counterpart, even though there have been tons and tons of sources that are potentially suitable in the sense that they could have been associated with the counterpart. So we haven't done very well. So there is probably reason to believe we could do better. And in trying to answer what we could do better, it may be beneficial to sort of walk you through what's actually happening in the discovery space right now. And we can think about solutions creatively. I have one solution. It's not the only one, but we can do things better. And of course, it'll be biased in terms of like, I'm going to nitpick and I'll show you where the limitations are. But of course, there are probably other things that are not so state of the art. Okay, so let's imagine it's May already, because that's when the next observing run will begin for the gravitational wave detectors. And there's a source in the sky, somewhere in the universe, which consists of 2 compact objects that merge and send out a signal into the universe. And this is a multi-messenger source. So this was detected in by ground-based detectors, but also perhaps like a space detector, which will receive prompt emission, if any, from this source. And what happens is that we have these amazing sets of like cyberinfrastructure pieces that will will receive these alerts and will pass on via various alert systems. And I'm primarily thinking of something called GCNs with some metadata about, what this signal was all about. So it will consist of things like, oh, when did this event happen? Where broadly in the sky did it take place? For example, in some cases, you may even know things like how far away the event was. So with all of this information, people get prompts and alerts about such an event taking place. And I think the time scale here is kind of important, is that in the matter of minutes to hours, that information is now processed by humans, processed by automated infrastructure that have been designed to respond to that information. And so at this step, for example, something else could happen. Surveys like ZTF could start tiling that particular region of the sky. So say, for example, here you have the blue region, which is sort of the broad localization region in which the merger took place. ZTF could go through with its own algorithms and try to sort of get more data points here. And again, I think this time scale here is important to remember that in the matter of minutes, this information is processed via automated systems to perform some sort of vetting. There is there's a first order algorithm called a real bogus classifier that looks through the images and tries to figure out which of the new alerts that we're receiving are most likely to be real. And just to mention, I think this is not appreciated enough. The real bogus classifier was and remains to be one of the biggest success cases of applying machine learning in astronomy, and was one of the cases that actually really demonstrated to people that we should not be looking at hand-tuned methods for performing tasks at scale, especially for things like, where we have large amounts of data. Another thing, for example, could happen is that you may reject sources that are already known. So we're talking about things like transients. So these are things that haven't happened before. So anything where you have previous variability, you want to reject them. This is not a good choice if you're thinking about any other messenger. So for example, if you're thinking of neutrino counterparts, this is not a good criterion and it's not actually used. But since we're focusing on gravitational wave counterparts, you may want to use this. Then again, for example, you also look at the light curves and you see sort of how the light curve is evolving, and with cuts that you can apply at this stage, again, within the matter of seconds to minutes, some 50 or so shortlisted candidates are left behind. And at this point, we send it to people. These would be early career astronomers, so advanced graduate students or postdocs, who will be thinking about these types of candidates. And their goal is that they want to figure out which one the real event is. And they want to take some amount of follow-up budget that they have set aside from other sources to acquire more information about the 50 candidates to tell you which one the real source is, and perhaps tell you what type of physics was happening in that explosion. And at that point, humans keep making decisions on trying to figure out which one the real event is. They may, for example, take into account any updated estimates for the sky map that you may get. You may think about, any host galaxies that are present. And at the end of this process, by the way, and I think, again, the time scale here is relevant, at the end of 1 week, less than 1 week, you may end up with a situation like this. And, you can stare at this a little bit. You can see there is like just a few amounts of measurements that were actually taken for the light curve. This is actually a success case. It is not a kilonova, but it was a success case for actually finding a very novel type of fast transient. But the idea is that at the end of this 1 week, here are the number of data points that we were able to successfully get, because look at the time scale of evolution and how faint some of these events can be. So this is a very, very challenging problem. So this is kind of a leading question, because I already pointed out that I don't feel like something is happening efficiently here. So let's focus a little more on this part and try to see what is actually happening and what we could do better. So as I mentioned, 50 or so candidates are received by networks of humans who at odd hours in the night will use communication platforms like Slack and Zoom and consider situations like these. So here I'm showing you 2 candidates There can be more, there can be few tens, there can be hundreds, but I'm just showing two to contrast them. What you may see is something like this. So here, for example, is a little cutout of that region of the sky that shows you the real source. Here is the reference image that shows the source is not there. You don't see the host galaxy here, for example. Just ignore the y-axis for now. But what you're seeing is there's no detection. So there's some upper limits here. And then boom, you see something coming up in terms of like the measured photometry. You also see this for this other transient. And without any other information, it's kind of hard to know what the real source might be. You may have some inference, some expectations in terms of what the light curve could look like from just basic physics principles. But apart from that, it's very hard to tell what actually is the real event. And if then you think about what these humans are tasked with doing, they basically have to use very limited resources that they have been trusted with at detectors that are positioned worldwide to acquire more information. So they have to get more data points in addition to what the survey is doing to identify which the real counterpart is. This is a very hard problem, even from the classification perspective, because if there are 50 or so candidates, the true event, the chance that you will select the true event is less than 0.05. And I say less than 0.05 because it's possible none of them are the real event. So we need at least some amount of machine learning solutions to help us solve that problem of identification. But honestly, that's not the only problem we want to solve. If we are going to spend resources in collecting more data, we want to make sure that the data is sort of meaningful for the types of physics inference we may want to do. We may have some target models. We may want to actually do parameter estimation. So the data points that we do get, so the additional follow-up that we do get should be constraining for the parameters that we may be interested in. So here are two bold statements that I will make. The first one is that additional follow-up is critical. And the reason I state this is because people have gone back in time and have done after the fact searches for the real event. And the data set as is in terms of like whatever had happened and what the survey collected was not enough to identify the real counterpart. So you need to have more information in addition to what is being collected to help us answer the question of, to help us identify which the real counterpart is. The second assertion I'm going to make is that using classifiers does not help you all the way. For example, using a classifier where you probably have a ranked list of events with some amount of classification probability, it doesn't answer for you what you're supposed to do in response to this, which means that if you receive the highest probability classification of 0.47, does that mean that I actually should allocate follow-up to this one? Maybe the better strategy is to allocate a follow-up to something else to rule it out at that moment, and then do something else when the observing conditions improve or you have more constraining epochs that are coming up. And even if you could probably do that, which particular set of observations should you take, in what cadence? So there's these questions about that sort of leave you with more question marks that I don't think are being addressed. So there is this need for decision making around using data science infrastructure that is not present, and it's completely critical in my opinion. So essentially, I'm going to argue that whatever process needs to happen here that makes the process more streamlined needs to be free from fatigue and bias. This is a process that I feel is very exhausting, and we shouldn't expect experts to spend a lot of their time doing this. It should also be low latency because we don't want to wait several hours and days, in fact, to trigger and obtain follow-up information. And whatever process that needs to exist needs to also be scalable. And the last issue of scalability is very important, because I should note that I was talking about May already, and and this is because the gravitational wave detectors at that time will start operating at about twice the sensitivity. And the expectation is, compared to about 20 individual gravitational wave triggers received, this time there will be at least 2 times or 10 times as many individual triggers for gravitational wave individual gravitational wave triggers that will be picked up by the detectors. At the same time, the search regions, so the localizations regions I'm showing, will not improve very much. So if you think about the previous infrastructure, you will actually end up spending maybe you will have 1 or 2 individual triggers per week where humans are trying to figure out, can we see if there's the real kilonova or not. And the other issue is that I said there's a lot of excitement about Rubin coming online, but this will also start posing challenges because the current surveys are operating at about about an order of magnitude lower than what Rubin will. So when Rubin comes online, we will receive 10 times as many candidates that are posed for humans for analysis. So if I go back in a second, for each individual gravitational wave trigger, instead of having about 50 candidates, you will have 500 or so to decide which one is the real event that you want to follow up on. And at the same time, the follow-up resources, so any smaller telescopes that we want to get photometry with, any spectroscopy that we may want to get, is not going to increase at nearly the same rate. So this is my final bold statement before I get into my solution, which is that the current protocols that are being followed are neither sustainable nor suitable to actually get at the statistics, which is to actually get more and more of these novel event types that are very exciting. Yeah, something needs to change essentially. So I'm going to pause right here to see if there's any questions before I move on, because right now I'm going to talk about some solutions that we have.
So does anyone have any questions for Niharika at this point? Or are we all dying to hear her solutions? No, I think.
All right. Yeah, I'll keep going. So essentially, I've created, what I've said in so many words is essentially that if we want to stitch together a decision-making system that responds to machine learning, not enhanced, augmented information, we need something more. And if we think about making decisions in real time that are autonomous, we will find ourselves thinking about the class of problems that I'm going to introduce now. Decision making under uncertainty is a problem that all of us face in our lives all the time. We don't know what the future looks like, yet we want to, based on probably other people's experiences or what we know about ourselves or the worlds around us, we want to make good decisions, even though we don't know how our decisions will look like in the future when we get more information. In the classical setting, this is known as design of experiments. This is a field that was pioneered in the early 1900s by Christine Smith, a mathematician. As with most machine learning solutions, the thing to note is that the algorithms and the methods behind some of the stuff that I'm going to talk about predate the early 2000s by decades. So these are not new and in any way. In contemporary machine learning, these are dubbed as either reinforcement learning or optimized sensing, depending on which community you're talking to. So if you're talking about the computer vision community, you're probably thinking about optimal sensing. If you're thinking about the robotics community, you're probably thinking about reinforcement learning. And the thing to sort of highlight here is that of the various types of machine learning solutions that we have seen proliferate the space, there is this very famous plot by Andrew Ng, who is one of the big names in data science, who made this plot back in 2016, which was a very, very big year for deep learning approaches. And said the following, that if you think about commercial successes, so he was thinking about industry applications, his projection was supervised learning would be the area of fastest growth in terms of what would proliferate the fastest, followed by transfer learning approaches, then so unsupervised learning approaches, and the thing that was sort of like the most slow burn, if you will, is reinforcement learning, which is sort of like the area of highest, most long-term projected growth. And I think I was actually surprised because, in the this year or so, we've actually seen that realm change a little bit. So how many of you are familiar with ChatGPT? So I mean, if you're raising your hands and I don't see you, I'm gonna say most of you are familiar with it. And the thing to note is that the reason why it was very successful and it has been better than other chatting agents that solve similar problems is because underlying all of the other types of algorithms that help it make inference and do generative modeling is reinforcement learning. So the underlying sort of interaction based, like adaptive formulation is based on reinforcement learning. So I actually found that surprisingly, I felt like the development actually happened faster in terms of what was more successful. So the thing to note is that reinforcement learning is a very significantly different domain than supervised learning. It is not something that you can immediately have a student pick up without taking additional coursework. And I feel is one of the main reasons why people have not we've not seen as much applications in academia for that. Not academia, and for people who are usually applying data science, we actually don't see people use reinforcement learning because the training is not there. And this is a significantly different domain in terms of the algorithms and the formulations we need to solve the type of problem. Okay, so with that being said, how would you solve a problem like the one we're talking about? So let me focus on a toy model and a toy agent to just introduce some very basic principles of how this could look like. And the thing to note is that we are no longer going to be talking about things like training data. We are going to be talking about things called Markov decision processes, which are sort of like a series of state, action, rewards, state action, so on and so forth, that an intelligent agent is going to experience and try to, using it experience, come up with ways to make decisions such that it maximizes the designated objective. So we're going to go through that. So I'm going to apply this particularly to the type of problem that we've been discussing so far. So, it's going to be very problem specific, but there's no reason why, as with any machine learning problem, this cannot take a different version, which is more suitable for another type of problem. So here's what we have. We have now subbed our graduate students with a little robot that is going to think about the following situation. Here we're going to give it just one light curve. Okay, that's it. I'm saying 50 Canada. I should probably fix that. You're going to give it just one light curve, one particular data point. And I'm going to give my agent some resources, and I'm going to ask it to collect more data such that it can, such that the additional data that it acquires maximizes an objective. This objective can be anything. It can be to say, identify whether what you're looking at is what you're looking at. Or for example, it could be take whatever data point that you're going to get and make sure that that additional information is going to maximize constraints on some target model that I specified to you. So this could be the setup. So how would the agent solve such a problem? The first thing that the agent wants to do is specify something called a state space. Now, the state space is really just a mathematical or a vector representation of the world that the agent experiences. So, for example, if we are thinking of presenting the light curves, you could just give it the multi-channel light curves that we were talking about, right at the front of the right at the start of the talk. Another thing you could give it, for example, could be images, the image cutouts of the region of the sky itself. So any form of vector representation of whatever the agent is interacting with is known as the state. Okay. So the second thing you want to do is specify the actions that the agent can take. So for example, in here, we are thinking of light curves that are in two filters. So we have the G filter and the R filter. These are, by the way, from my bias of ZTF, which has two public filters. Which has a public survey in two filters. So for example, the action that the agent might consider would be to take an additional data in G, take an additional data in R, take an additional data in G and R, or it could do nothing. So the arrow, by the way, indicates the time stamp at which the agent exists. The thing to note is that in general, actions don't have to be discrete like this. For example, I could specify for the agent saying, here is a total number of observing hours or how much time you could spend on the target. figure out how much time you want to sit on a particular target and get that particular measurement. It can be stochastic, which is kind of important because you could have a situation where your actions, even if you took an action, you may not be successful at actually getting anything out of it. This is often the case, not often, I don't know how often this is the case, but it can happen in astronomy where we try to get follow-up observations, but you could have detector problems, you could be clouded out, whatever reason, for whatever reason the image was not well reduced, you would not end up with any data resulting from your actions. So you should in principle be tolerant to a situation where even if you try to take an action, nothing would come out of it. And you could do this in reinforcement learning. You could impose notions like cost and a total budget. As I already mentioned, you can have a total observing cost, and each particular observation could be associated with a different observing cost. For example, if you want to get spectra, that would be more expensive than probably getting a photometry. And you can specify how much do you think you want to say, you value one versus another. Great. So that's step 2. Step 3, you want to say that if I take a particular action, what would happen? So like, for example, here, the agent is sitting in this timestamp and is thinking of taking an action in R. And the particular probability distribution of where it ends up as a result of taking that action could be the set of next states that the agent could encounter. This is in reinforcement learning, in the language of reinforcement learning called dynamics, or the transition model, which means that from one state, how do you transition to a different state? For our case, having solutions that are robust to stochastic transitions are important because we usually have surveys that are non-deterministic, which means that, say, for example, you expect to collect some amount of photometry later on, we don't know when it's going to happen. So if we want to make good decisions, we want to make good decisions despite stochastic data products that we may get as the survey is operating. And this is possible in reinforcement learning. So yeah, that's what I was saying here. In general, your dynamics model can be, the transition model can be unknown or it can be stochastic. Another way to think about, there can be 2 types of transition model that you can have. It can be in terms of what data you might get and in what schedule, or it could be, for example, the underlying physics model, where sort of what the outcomes may look like given a particular physics situation that's happening. Step 4 is basically estimate, if I get a certain outcome by taking a certain action, how valuable is that to me? So this is the specification of your science criterion. So as I mentioned, you may want to say 1 or 2 things to the agent. You may want to say, identify if this is the real event. So for example, you may want to say, for this one event, if I take data in R, in this case, what is my improvement in my classification accuracy or my F1 score or anything like this? If you were after the physics question, you may say, given the set of outcomes, how much am I expecting to improve in my physics model parameters? You can also take a compound situation where you can go after one of these things. All of this is fine. In general, again, outcomes can be stochastic. Typically in physics, we won't see this because you usually get a deterministic reward. But I think in general, you could actually have stochastic returns. For example, if you were trying to solve the multi-amp bandit problem, where you have slot machines where you're pulling various levers, the reward a particular slot machine will give you will be in general from underlying reward distribution. In physics, this is not the case, but again, reinforcement learning approaches can be tolerant to that as well. Number 5, you have to do something based on all this information. This is called policy. In some sense, basically, like if I'm in a certain state, I have a bunch of actions, I think I'll end up in a certain situation, and how useful that would be, what should I do? So let's imagine in this case, my toy agent is going to do something really silly. It's going to be very greedy. It's going to do whatever is best right now. It'll look at the rewards it'll get for all actions, and whatever myopically at this moment will do well for it is going to do that. This is known as a greedy policy. It's not ideal in the most general setting because it does not take into account any other thing it may do in the future. So in reinforcement learning, we are usually thinking of making optimal series of decisions. We see something, we take another decision, we get more information, and so on and so forth. If we do something that's locally optimal, we are not thinking about whether the current decision was optimal given anything else I might have done in the future. So this greedy policy is a simple way of running an algorithm. In fact, our very first formulation used a certain type of a greedy policy. In general, you don't want to do this. In general, you use something called a Q function, which is basically saying, given the particular situation that I'm observing, what is the current reward plus a mathematical notion of what we obtain in any future behavior that we may get. So it's the current reward plus something called a discounted sum of future rewards. And you learn to make good decisions in terms, like you iterate through it and you actually learn the best Q function that represents Q. I think of Q as often quality. I'm not sure if that's the case, but Q, you can think of Q being like, given a certain state and a set of actions, what is the best quality action I could take? And a greedy agent would typically take the best action locally, or a better reinforcement learning agent would iterate and learn what the best Q function should be and generalize. Okay, great. Once you've taken a certain action according to your policy, the next step is to adapt to any new information that you receive. So for example, in this case, the agent chose that the best decision it could take according to its greedy policy was to take data in R. So it took that data, it got a particular observation, and it finds itself at the next time step. You will keep going through this process until one of the following conditions are met. Either the episode ends. So for example, in our case, it could be the transients now too faint and you won't see it anymore, or that you have exhausted your budget, or in that you don't have any more data that you can take, or you can repeat this forever. And all of these are completely fine. So essentially, this is reinforcement learning in a very, very short nutshell. Matthew, am I bad on time? I feel like I'm really bad.
You've brought maybe 5 minutes or so left. So
I actually just have gone through half my talk. Okay. All right. You know what? I'm just going to focus on the main problem at hand here. So what we've been thinking, so we're thinking about collecting data. We're thinking about identifying kilonovae counterparts to gravitational waves. There's some just brief introduction here. So what we have developed is something called Pythia, which is a reinforcement learning agent that does this, solves the problem of allocating follow-up to try to identify the real event. So this is just a classification analog of an adaptive agent, basically. And here's the situation that I presented. You will receive 9 transients, of which one of them is the real kilonova, and the rest are all contaminants of various types. They can be things like supernovae, unassociated GRB afterglow, shock breakout, etc. And you get to take one additional data point in one filter with a very long exposure. And you get to do this every day for 6 days. You get a reward 1, which means you do well if you have allocated that budget to the real event. Otherwise, you get a 0. So you can think of this as like some sort of a target practice situation. There's a little bit of a caveat on this particular reward specification in that we wanted to make it as model agnostic as possible, because for novel transients, we probably don't want to impose too many model constraints, but this is something that, as astronomers, we may need to work out. So let me just show you really quickly, actually. So this is the algorithm. This is a full reinforcement learning agent. Ideally, I would actually walk you through it. It's fairly easy. Basically, you take the Q value, and I have just linearized it. And I said, given a representation of the state action, learn weights W such that when I actually take a greedy action, this particular value is maximized for the best action. So you learn Q according to this particular algorithm, which is very standard. It's one of the simplest things you can do. It's very easy. So anyway, what we had is the following situation. We basically had, like I said, so okay, let me just explain what this is. So on the left-hand side is a bunch of episodes that the AI played, in that each of these episodes consists of 9 light curves, as you can see. The real event is being highlighted in this way. And the light curves, as you can see, are in here. The little crosses are the additional follow-up that was allocated by the agent. The thing to note, and these on the right-hand side is the same type of procedure that was repeated for humans. And what we found is essentially for the same type of problem, we ran the AI versus several human experts and non-experts. So we had astronomers and who are sort of non-specialists in the multi-messenger space and multi-messenger experts who are probably published in this domain to try to solve this problem, basically allocate the maximum number of follow-up observations to the real event. And what we found is that for this very simple agent, all humans did really, really well, up to 2 times as well. Basically, right now there's no threat from AI to actually replace humans for this type of problem. But the thing I want to mention in the very little time that I have is that we chose this very simple particular hypothesis. We chose a linear hypothesis. It's known as linear value function approximation. It's like doing linear regression in reinforcement learning. And the reason we chose it is because we are guaranteed to converge the optimal Q function. So we wanted to make sure the whole point of doing this exercise was to demonstrate learnability, which is that this problem is something that can be learned by machines and actually solved by machines. And what we find is that this is the learning agent. Here is the human benchmarks. It definitely does better than random, but so far doesn't do well against humans. And we're basically thinking about how to make this real easily better, which is something called deep Q networks, is again deep learning in reinforcement learning, which is also like fairly easy to accomplish once we actually have the thing set up. Anyway, we spent a lot of compute getting this to happen. Just want to be honest about a little bit of our carbon footprint. We emitted about 1,210 kilograms of carbon equivalent, which is equal to 1 round trip flight from LAX to JFK. Reinforcement learning is very computationally expensive compared to some of the other approaches that people usually think about. So we have to be careful when we design some solutions and we run our code. So we are so essentially, like, I'm sorry, like, I went through too much of the detail without going through the science stuff, but essentially the idea is that having such sort of a human machine interface can actually help us get to samples with large to get to diversity in kilonovae with large samples and prepare for Rubin in the future. And as such, I just want to mention that when we use reinforcement learning, we are doing 2 things. One, we are actually closing the gap between inference and decision making, which is currently lacking with just vanilla machine learning approaches. And the second thing we are doing is that we're reducing the burden of tedious work. So well-defined science cases that can be easily generalized, we want this to be solved by humans as best as possible, so we can leave innovation and discovery to human beings. And I leave that with a question mark because this is actually unknown. So I think this is not as well appreciated amongst us in the natural sciences, but this whole question of whether machines can actually solve an innovative question answer an innovative question or lead to discovery is something that we in the domain sciences will be the people who are answering. So while up until now, it's unclear whether this can happen, it remains to be seen. But I think approaches like this will be useful regardless as we move forward. So yeah, thanks for your time. I'm sorry I couldn't get to the science. Happy to talk about it whenever you want, but I hope at least some of the ideas were useful, because that's really the point, is to think about ways we can do some of our science better with these algorithms. But yeah, I'll stop right there.
Great, thanks, Niharika. Okay, we have time for some questions if anyone has any questions for Niharika on this. Or you can prompt her to tell you about stuff you didn't hear about. Andreas.
Yeah, hello, Ari. Very nice talk. Thank you very much. And a very hot topic. So I was wondering a little bit, at the beginning you showed, so to say, the pipeline of activities, and starting with a gravitational wave or with a merger, and then you had I wonder a little bit that this is going, so to say, in one direction, so to your problem. I mean, on the other side, the question is, I missed it somehow. So when you find, so to say, interesting light curve or a survey or an interesting event, so in principle, then everything should go also in the other direction to make alerts, so to say, to other facilities and other telescopes, and maybe also to for example, to IceCube. And so have you just not discussed this, or is this automatically included, or would that be, so to say, require a totally different approach?
So tell me if I'm misunderstanding your question. You're saying you want to make sure that when we are making decisions or when we are making discoveries, we are connecting with other messengers, especially in neutrinos. Is that the question?
Yeah, for example, yeah, exactly. That means exactly this arrows in the other direction. But this, of course, requires a very fast and a real-time analysis from your side.
Yeah, I am actually not very well positioned to answer this question. Thankfully, there are tons of people here who are. I'm going to say just one sentence, which is that I think that, people are at least aware of the opportunities here and the infrastructure within the groups of people who are thinking about the science. They will be aware of it. But I'm not sure if there's any formal, sort of communication from Kilonova search experts with IceCube specialists. But there is who else? Eric is here, Michael's here, and okay.
Yeah. Oh no, I'm not up. Go ahead.
No,
No. Yeah.
if you want to respond, Michael, please do.
Okay. Yeah, I mean, this is one of the, let's say, shortcomings of sort of the way these collaborations are structured, right? So, we are lucky in some sense that, focusing on ZTF for a second, that we have pretty strong integration with folks both in IceCube and in the LVK, all within this optical follow-up collaboration. Within, sort of speaking of LIGO, right, there you have subgroups that do have, the joint IceCube searches with the Columbia group, and then, the searches with Fermi and Swift, kind of the GRB subgroups. But yeah, the challenge is that there's not a lot of public fora for these conversations to occur. So in practice, they kind of, occur behind closed doors between people who happen to be part of these collaborations. And so to me, this is one of the opportunities A3D3 has. It's one of, let's say, one of the broader contingents of at least formalized collaborations across at least some of these bigger multi-messenger experiments, and which is why, we benefit greatly from that. But yeah, I think until there is, even, let's say, more public ways for these groups to interact, I think this will continue to be kind of an open challenge.
Yeah, no, I see this, of course, and just looking to this slide here, I mean, 1 week, of course, is somehow a problem, but I was wondering that the third last step is also seconds, can be done within seconds. So I was wondering if one can turn around it and say, okay, if we have, so to say, as a possibility in real time to make decisions on a second time scale, then of course one could also send an alert, not only receiving alerts, but also sending alerts in near real time. That was just my question, if this is also considered here, because of the crucial point is, so to say, to have really this very fast machine learning classifier and selection and decisions. And then if this is possible, then one can turn around the arrows and also going back. But thank you. Yeah, nice discussion.
So I'll add my my tuppence worth for that, Andreas. I think in the community, people have been thinking about real-time alerts and all this for about 15 years in the community, and we're really only at the point now that we actually have data streams where we can do this sort of work and combine it and think about these low latency problems. So I think there's always been an element of there involved, but we haven't had the computational infrastructure really to drive a lot of that. And it's only now with this sort of work that Niharika is thinking about with real-time decision making, and we can take the humans out of the loop, and so we can really improve the speed on this decision making. Right. And ultimately, you could imagine that you could have, a system for each experiment which is doing it, and then those systems start talking to each other, and then there's some coordination system. So I mean, you can see the roadmap for how we take the humans out of the loop and move this all into intelligent agents discussing with each other or communicating with each other, in some way like that. And so I think it's just, it's going to happen. It's just when, and and as Michael is saying, there needs to be also this sort of more public accountability or public viewing into this.
Yes.
On the project side to say, look, we're going to be putting this out, and you go and go, okay, we can take that and merge it with this and do this and these networks. And so I think, you know, there is a vision there. And I think this is, you know, this is a very important work for establishing that. But yeah, the other problem is, of course, do you trust the decision, particularly with an expensive resource that you may be using for a follow-up observation, that the AI system is going to make for you? And there will always be people who don't. So, I mean, you know.
Yeah, but that's learning. But that's already nowadays. Nowadays, the alerts are quite rare. And then still humans are just sitting there, operation managers of telescopes and so on, and thinking about, should we go there in this direction or not?
Yeah.
That is also not a very trustable
way.
No,
exactly. So, I mean, you know, so that is...
No, but I'm very happy that you see not this only as a vision, but also as a mission. This is the first step.
Yeah.
It is a mission to provide the tools and the services, and then one can really follow the vision.
Yeah. I mean, it's all about, you know, part of it, I think, and, you know, not to put words into Niharika's mouth, but it's all about, you know, it's optimization, right? And we have things, we have limited resources, and what is the most efficient way we can use those for doing scientific discovery?
Yep.
Yep.
Thank you very much.
Yeah, and in terms of reliability, by the way, when I presented the results I was showing for human benchmarks, in my mind, if I could show that for the same problem, blinded in some way, you know, we do better or not against the machines, that should be enough to convince people that this is something that we must do. If I could get the numbers right, for me, that should have been enough. But surprisingly, it was not. So when I shared these results, I got resistance from people who would, you know, who are invested in this, and not for malicious reasons, but just because they will be like, oh, but what if there's something novel that, you know, we can't adapt to? Like, you know, this is learning from simulations. And what if we need to respond and like, you know, the agent does something unoptimal? And I think the answer that I gave was two. One is that I'm not arguing that we will do better when there's something novel necessarily. The whole generalization issue of machine learning is a big one, and we don't want necessarily to apply algorithms where you won't generalize better. But secondly, if you actually talk, which we did, to these experts and ask why they did, what was their strategy, more often than not, you will find that they were relying on whatever their prior knowledge was from the physics side. So in some sense, they were biased too. So like it's going to be, in my mind, a huge challenge from, like you mentioned, the infrastructure, but also like the adoption side, because this is so novel that I think I will, and, you know, other people who want to support something like this would have to jump through to make sure that people actually be like, no, you know, this is what we need to convince ourselves, and at this point we do trust it, and it's okay. So yeah.
Good. Okay. Thank you everyone for attending. We're 5 past the hour, so I think we can stop recording at least.